Good evening, everybody. How you doing? This is Coach Scott. We're going to start getting into the really cool stuff. We're going to start talking about the quantum model tonight, and now we're really getting into chemistry. All right. So, the quantum model of the atom. We talked about the Heisenberg uncertainty principle in the last video. So we can't say exactly where an electron is at any given time, which means that the Bohr model with the electrons in neat little orbits can't be correct. So quantum theory describes an electron probability distribution, or where there's a 95% chance that that's where that electron is. And you can see this model right here. This is the probability of where this model might be, or where the electron. Okay, and so this little cloud, if you would, there means that there's a 95% chance at any time that those two electrons or one electron is somewhere in there, in that cloud. All right. And we're talking about for the ground state of hydrogen. So it only has one electron. So you've got a 95% chance that one electron is right in there. Boom. So in this picture, you can see that the probability of finding the electron, it's represented by the density of the dots of at the location, right? Let's see how I can do that. Okay. So according to Schrodinger's wave equation, our solutions to the wave equations, we're not going to get into those equations because that is extremely high level math. There's sets of numbers that makes his equations work. So there are 4 different quantum numbers that we put in to make those equations work. It's the N number, the L number, the ML number, and the MS number. And you need to know that there are those 4 numbers. We'll do a little activity and we'll talk about what those numbers are, and so you'll have a familiarization with them. You don't have to necessarily know them exactly, okay? You need to have a familiarization with them, so when you take additional classes or you hear about them, you'll know what they mean. So these 4 quantum numbers are needed to specify the state or the probable location of where that electron is in the atom. So the first number is the N number, the principal number. And what the N number is, the main energy level or the distance from the nucleus. So you've got their whole numbers, 1, 2, 3, 4, similar to the Bohr model, but there's various levels of this, right? So that's your electronic energy level. That's what we'll call it. The L number, we call it the angular number, and that describes the shape of the orbital. And we're going to talk about this today. The ML number is the magnetic number, and it describes the orientation of the orbital in space, or where it fits around the atom, or in the atom. The MS number is the spin number, and that's pretty easy. There's only 2 of those, and that tells us what the direction of the electron spin is. And we're going to go into these in more detail. So let's talk about the principal number, N. Similar to what Bohr called N, the principal quantum number is an orbital, is a region of space where that electron is most likely to be found. So that principal quantum number N, it'll describe the energy level of the orbital, which we usually call the energy shell. All right. So the values of N are integers greater than or equal to 1. So it's like 1, 2, 3, 4, 5, not 1.5, not 2.5, not pi. It's 1, 2, 3, 4, 5. Now, the larger the value of n, it usually means that the further from the nucleus the electron should be found. Okay? So let's take a little check, make sure we're at. So the principal quantum number n determines the energy of the orbital. The energy of the orbital, B. As n increases, the orbital energy, what do you think? Take a pause and we'll see. And of course that's A. It'll increase as the shell increases, the orbital energy also increases. Now let's talk about the L and the ML number, the angular quantum number and the magnetic quantum number. So we've got the shells, and underneath each of these regions there's subshells, and each of these subshells has a very specific shape based on the energy of the electrons occupying them and their specific orientation in space. So the L number designates the shape of the orbital. And we're going to get into this pretty heavily. There are 4 shapes of orbitals. There's an S shape, a P shape, D shapes, and F shapes. ML will tell us what the orientation is of the orbital in space, or the subshell in space. So we've got the L number, gives us the shape, 4 shapes, then we have the ML number. So these are the shapes. And we've got models in class which we'll go over. The first shape is the S. You can think of that like sphere or ball. All right, so there's only one orientation for this. These are the P shapes. They're dumbbell type shapes, and they're aligned along the X, Y, and Z axis. Okay. These are the D shapes. So they're pretty weird, but I've got some models of these, and we'll look at those and touch them and feel them, right? So these are the D shapes. There's 5 of those. These are the F shapes, and they're really strange. And you can see that, well, there's 7 of these. Now let's see if we can see a pattern. 1, 3, 5, 7. That might come into play later. Okay. So the S orbital, or the S subshell, they're spherical in shape. S for spherical. And the radius of the sphere will increase with the value of the n. So 1s is much smaller than 2s. And then 3s is much bigger than 2s, which is bigger than 1s. Okay? Now, it doesn't matter about the ML number because there's only one orientation in space, a sphere or a ball. Okay? So, the L number for the S space, it's got one orientation, and it's only one orbital per energy level. Now, the P subshell, they're pretty cool. So, the P orbitals have 2 lobes, and there's a node around the nucleus between them. So, for P orbitals, the electron density and the probability of finding the electrons depends on both the distance and the direction from the center of the atom. So, as you get further away from the nucleus, you have a higher probability of finding the electron. Okay? And toward the center, you got a lower probability of finding the electron. Now, does that mean there's an electron on this lobe and an electron on this lobe? No. It means there's 2 electrons that can hang out there, and they can be anywhere in that region. So, there are 3 subshells to the P subshell. There's 3 possible arrangements or orientations in space. So there's 3 orbitals. Now we sometimes, the official quantum number is p minus 1, p0, p1. Sometimes we'll call these px, py, pz. You'll see those. And that just tells you where these lobes are oriented on a XYZ axis, or a 3-dimensional axis. All right, so the L number is the P shape. There's 3 orientations, so there can be 3 orbitals per N, or per energy level. Okay. The next one is the D subshell. Now these are complex. Okay. You've got these, I don't know, look like spaceships or whatever, or yeah, they're pretty cool. Now there's 5 orientations in space, so there are 5 possible D orbitals. So the L number would be, well, 3, but it'd be the D shape. There's 5 orientations, there's 5 orbitals. You can see the quantum numbers are minus 2, minus 1, 0, 1, and 2. Okay. The F subshell. I can't draw these on the board. I can't draw them in a planar way. But you've got 7 different F orbitals, and I can't even begin to describe those shapes. What does that mean? These are the areas where that electron, or that electron pair, can be. They can be anywhere in that area. Keep that in mind. So the L would be F-shaped, the ML would be 7 orientations. We'll find out minus 3, minus 2, minus 1, 0. Those are the quantum numbers for the F shape. So let's take a quick check. The quantum number L determines the what? Pause, pause, pause. And of course the answer is the shape. L determines the shape. So let's see, what does ML, the magnetic quantum number, determines the what? Pause. Well, of course, that's the orientation, A. Where does it line up on the XYZ chart? Now, which one of these orbitals is lobe-shaped? Pause. And of course, the answer is B, the p orbital. So an s orbital has how many possible orientations in space? S stands for pause. Sphere, so there is only one orientation in space for an s orbital. The f orbital, on the other hand, has how many possible orientations in space? Pause. And the answer is D, 7. Okay, 7. So, we've talked about the N number, the principal quantum number. We've talked about the angular, the magnetic number, and the angular number, ML. The last quantum number is the MS, or the spin quantum number. So in 1920, it was discovered that 2 electrons in the same orbital do not have exactly the same energy, though they are electrons. So this led to the 4th quantum number, the spin quantum number. All right. So what it's saying is that the electron has either a right-hand spin or a left-hand spin. Okay. So the spin describes its magnetic field, right or left, and that affects its energy. So the spin quantum number can be either positive or negative. So this implies that electrons are in some way able to pair up, even though they repel each other because they're both negative charges due to Coulomb's law and the electromagnetic force. So write this down, put this in your notes, whatever. Each orbital can only hold a maximum of 2 electrons, one with the left-hand spin, one with the right-hand spin only. Write that down. So the spin quantum number ms, pause. Of course, the answer is D, A and B. It can only have two values, and it relates to the spin of the electron. So electrons within the same orbital must have, pause, must have C, opposite spins. They cannot have the same spin. Okay. So let's see what else. So guys, that concludes the preliminary quantum structure. That's the basics, and that is our quantum model, or what makes up the atom. So we're going to dive into this a little bit more tomorrow. I'll have another video out for you. So guys, this is Coach Scott saying, have an awesome day and deuces.